This is our cantilever beam analysis from Team 1. My name is Kevin Barnett.
My name is Haley Hunt.
And my name is Andrew Cobb. Enjoy the presentation.
The engineering challenge we were faced with was to design the cantilever beam component of a frame on which various water quality test instruments could be mounted. The frame was to be used by Engineering Without Borders as part of a wastewater treatment facility in La Ceiba, El Salvador. The task was to find the type of beam that could be used to allow instruments to be partially submerged in a mangrove swamp on the project site. As with any engineering challenge, the solution needed to be cost efficient. Other factors to be considered were that the maximum number of instruments that could be clamped to one beam was 3, and only one of each beam type was available. The apparatus can be seen in the figure below.
The first step of the project was to determine the equation that best models the relationship between beam parameters and stiffness. To do this, we had to test 22 beams in the project lab. These beams fit into 4 sets. In one set, length was varied while elastic modulus, width, and thickness were held constant. For another set, width was held constant, and so forth. To test the beams, we added a certain amount of mass to the end of the beam and measured its deflection. 3 data points were collected for each beam. The data for varied length is shown in the table below. The second step was to use these data points to determine the linear relationship between deflection and load for each beam. The slope of this linear relationship was the K value, or stiffness, for that beam. The linear relationships for the set of varied length can be seen on the plot below.
In step 3, we created a log-log plot of the varied parameter versus the stiffness values found in step 2 for each of the 4 beam sets previously mentioned. Applying a power polyfit to these relationships revealed the value of the exponent for each parameter in the equation above. The example shown below is the set of varied lengths versus stiffness. The equation that best models the relationship is stiffness equals 17.2 times length to the -3. In step 4, we applied the value -3 to Q, the exponent on length, in the equation above.
After completing step 4, we only had one unknown variable, C, remaining on the right side of the equation above. When performing a dimensional analysis of the equation, we determined that the variable C would be unitless. We plugged the parameters and the stiffness of each beam into the equation and solved for the C value of each beam. A sample calculation for beam B can be seen below. This calculation was performed in our program for each beam, and the average of all the calculated C values was found. This average value was placed into the final equation. This final equation can be seen at the bottom of the slide.
This slide is a culmination of all the work previously done. We will use the equation that we have found to determine the most efficient beam to support the water quality test instruments.
The first table shown contains all 5 of the water quality test instruments along with the drag force that each one will apply to the beam. The second table contains the 6 available beams along with their dimensions, costs, and material types.
To determine the accuracy of our equation and program, we tested 4 beams in the lab. A known force was applied to the first 2 beams, and we used our equation to predict their displacement. For the second 2 beams, a set displacement was given, and we used our equation to predict the necessary force to apply. Both the predicted results and the actual results are shown in separate tables. Our percent error is shown in the third table. The cause for error is twofold. First, any time an experiment is performed, human error must be accounted for. The measurements are only as accurate as the human eye will allow. The second and probably more prominent source of error is material deformation. Not only were the beams used by multiple groups of experimenters this year, they have also been used by engineering students in many previous years. After so many cycles of force being applied, the beams will start to reach plastic deformation. Because the beams are already deformed and the stiffness has already been decreased, the data is slightly skewed.
Since we now knew the appropriate equation which best modeled the relationships between parameters and stiffness values, we were able to calculate the maximum amount of force each beam withstood. First, we recognized that thickness had an exponent of +3 in the discovered equation. This exponent showed that there was a direct relationship between the thickness of the bar and the overall stiffness. Since we wanted the least possible deflection, we decided to make the thickness greater than the width whenever possible. Although the width was directly related to stiffness, it only had a value of +1 in the exponent. For this reason, an increase in thickness would have a much greater impact on the stiffness of the beam than an equal increase in width. We were given the requirements that only 3 instruments could be placed on a single beam, and the total deflection for the 5 total instruments could not exceed 1 inch. With all of this in mind, our goal was to fit these requirements in a cost-effective manner. Since only 3 instruments could be placed on a single beam, and the sum of the greatest 3 instruments' drag forces was 9 pounds force, we chose the cheapest beam that could withstand greater than this value. We found that aluminum bar number 1 was the desired bar to hold the turbidity, velocity flow, and the nutrient meters. With only 2 instruments left, totaling 1.5 pounds force, we desired the cheapest beam that would hold more than 1.5 pounds force. We found that stainless steel bar number 3 was the most appropriate bar to hold the portable sampler along with the pH electrode. In total, by maximizing the force withstood and minimizing the cost of each beam, we found that aluminum bar number 1 and stainless steel bar number 3 were the best choices to meet the given requirements. By adding the cost of the 2 bars, we found that the total cost would equal $20.
To wrap everything up, we were first presented with the task of determining the most efficient beam structure that would meet the company's requirements. We began by finding the relationship between beam parameters and stiffness values. Then, we discovered the equation that modeled this relationship and plugged in the given beam parameters to determine the maximum load each beam could withstand. Adding this knowledge with the known cost of each beam, we determined the cheapest combination of beams that still met all of the given requirements. No other beam configuration could be more appropriate because the only cheaper bar than the ones chosen was aluminum bar number 2. However, its low maximum force withstood made it unable to even hold 1 instrument, and if used, a 3rd beam would inevitably be necessary. This would add cost, and the total cost would not be minimized. We hope you enjoyed our presentation.